Greetings, everyone. I am Uday Sharma from the Triple Department of Institute of Aeronautical Engineering. Today, I am going to discuss about the topic control of permanent magnet synchronous machines for subsea applications. Permanent magnet synchronous machines, or PMSM, are widely used in various applications due to their higher efficiency and power density. Subsea applications of PMSM include underwater vehicles, offshore drilling equipment, and subsea robotics. Controlling of PMSM is a critical aspect of subsea applications to ensure reliable and safe operation. The control strategies of PMSM in subsea applications are further discussed. Mostly, the permanent magnetic synchronous machines are used in like submarines, or drilling equipment in the subsea for the oil rigs, or subsea robotics, or subsea robotic arms, which are used to pick up things from the underwater. As we know, there is a platform which has a power supply source, which are travel to the long cables, and under the sea, it is connected to the PMSM devices, or permanent magnet synchronous machine devices. PMSM consists of a rotor with permanent magnet and a stator with windings. The stator windings are excited with three-phase AC voltage, creating a rotating magnetic field. The rotor with permanent magnets follow the rotating magnetic field, producing a torque on the shaft. The speed of the rotor is proportional to the frequency of the AC voltage applied to the stator winding. The output power of the PMSM is proportional to the product of torque and speed. Challenges. What are the literacy? What are the challenges in the subsea applications? As you know, as we have discussed earlier, we can see this is a subsea pump which is used to pump out the water in the subsea applications. Subsea environment pose unique challenges such as high pressure. As we know, if we go deep into the underwater, the more deeper we go, the more pressure increases on the devices. So the devices has to withstand higher pressure quantities than the normal devices. And deep inside the water, the temperatures will be also low. So they have to withstand or vary according to the temperature too. The main most reason is corrosion. When metals are advised or open to the water, they tend to decompose or corrode. So these three should be taken care of before installing in the before installing or sending the motors into the subsea level. Electrical insulation is one of the major components one of the major challenges to be taken in the subsea level. Electrical insulation of the motor and control system is critical to prevent short circuit. Cooling of the motor is a challenge with the lack of air and the presence of corrosive salt water. The communication between the surface control system and the subsea motor is limited by the length and quality of the communication cables. Let's say the communication cables are much larger or lengthier than required. So there may be a delay in the communication signal, or there may be a decomposed or reduced signal strength. The harsh subsea environment can cause mechanical stress and vibration, affecting the performance and reliability in the motor. As we know, as we can see here, there is a rectifier inverter and step up, which steps up the signal. As we know, there may be a losses, transmission losses of the signal during this bit. And here, the stepped up signal is stepped down and fed into the permanent magnet synchronous motor. Sensorless control strategies. Sensorless control strategies eliminate the need for mechanical sensors such as encoders or resolvers. Sensorless control strategies estimate the rotor position and speed using the measured stator current and voltage. Sensorless current strategies reduce sensorless control reduces the cost and complexity of the system and improves the reliability on the motor. As it reduces the mechanical devices or reduces the mechanical products used in the motor and becomes sensorless, it reduces the cost and complexity of the system and gives the final or accurate values of the speed and position of the rotor. So it improves the reliability of the motor. Sensorless control strategies include back EMF estimation, sliding mode observers, and adaptive observers. Sensorless control requires accurate parameter estimation and robust control algorithms. Let's see what is a vector control strategies. Vector control strategies control the magnitude and phase of the stator current to produce the desired torque and speed. As we know, the speed is mostly speed and or every electrical component is mostly based on the voltage and input current. So if we control the level of magnitude of voltage and current along with the phase given, we can easily control the torque and speed. We can easily control the speed and torque of the motor, and which gives us a precise instrument, precise locations or precise movements in the deep sea level. Vector control strategies use the mathematical model of the PMSM and the feedback from the motor sensors to generate the control signals. Vector control strategies provide precise control of the motor and enable fast dynamic response. As discussed earlier, as I have said before, the vector control strategies we ask it continues it controls the magnitude and phase. It gives us precise movements and dynamic response for the motor and for the instruments used in the subsea level. For example, if a submarine or a robotic arm is taken in the subsea level, it requires a precision location movement to pick up or something or for the exact movement. And the vector control strategies of the control of the PMSM motor provides us with that. Vector control strategies include direct torque control, field-oriented control, and space vector modulation. Vector control requires accurate parameter identification, complex algorithms, and high computational power. Let's see what is a subsea control as we have discussed. A power source is given, variable speed drive is connected to that. And as I have said before, a step-up transformer is given, which steps up the signal. And as the cable is kilometers apart from the main power source, it steps up the signal, which due to the losses and gets here, steps down according to the level of input of the PMSM, and the PMSM is connected to the pump. Here, like example, a pump. For the example, the permanent magnet single machine is connected to the pump. This is the example of block diagram of how a subsea control is used with the help of a PMSM motor. Power electronics. What are the power electronics used in the subsea applications of the permanent magnet synchronous machine? Power electronics are used to convert the DC voltage from the subsea power system into the three-phase AC voltage of the motor. Power electronics include the rectifier, DC-DC converter, and inverter. The rectifier converts AC voltage from the subsea power supply to the DC voltage. The DC-DC converter adjusts the voltage and current to match the motor requirements. The inverter converts again the DC voltage into three-pulse AC voltage, the desired frequency and amplitude. Control strategies for subsea PMSM. As we have discussed, there are multiple control strategies for the control of the permanent magnet synchronous machine. First is sensorless control, as discussed earlier. It is a control strategy that estimates the need for sensors to detect the motor's position and speed. The method uses algorithms to estimate the rotor position based on the current and voltage requirements. Vector control is a strategy that enables the decoupling of the motor's magnetic flux and torque control. It uses complex mathematical models to connect the motor's speed, torque, and position accurately. Direct torque control. Torque control is a control strategy that provides fast and accurate torque control without requiring the motor speed or position measurements. This method uses a hysteresis controller to select the optimal voltage vector to apply the motor. Model predictive control. It is a control strategy that uses a mathematical model to predict the motor's future behavior and adjust the control signals accordingly. That is, it predicts the future of the motor's behavior and gives the input signal accordingly. This method can be provided high accuracy and robustness for a subsea PMSM control. The PMSM control strategy should be selected based on the subsea application requirements and limitations. Subsea PMSM applications. In the subsea level, the permanent magnet motor applications include underwater vehicles, remotely operated vehicles, subsea robotics, and offshore drilling equipment. Underwater vehicles and remotely operated vehicles use PMSM for propulsion and control. Subsea robotics use PMSM for manipulation, drilling, and inspection tasks. Offshore drilling equipment uses PMSM for mud pumps, top drives, and drawworks. Subsea PMSM applications require robust and reliable control strategies to operate in the harsh subsea environment. The control of PMSM is critical for subsea applications to ensure reliable and safe operation. The subsea environment poses unique challenges such as high pressure, low temperature, and corrosion. Control strategies are used to control and improve the performance and reliability in subsea PMSM. Most of the power electronics are used. Fault detection and diagnosis and communication of the control system architecture are important aspects of subsea PMSM. Subsea PMSM has various applications such as underwater vehicles, remotely operated vehicles, subsea robotics, etc., and with a high potential for future development. Thank you. This is Sudeshama signing off.